Swayam Prabha. Digital India. Educated India.
We start from where we left, and we were trying to develop the relationship between emission and its impact. Okay. So if you recall, we're talking about the flux, okay, flux of the pollutant, okay. And first thing we said about the flux of pollutant was, number one was, which flux? Advection flux, okay. Flux due to flux of what? Pollutant, okay. Okay, and we define that as JA, okay, that was equal to CU, okay. And there was another kind of flux which we defined more because of diffusion, okay, more because of diffusion, okay, and that we call flux due to diffusion, and that we say JD, right, okay, that was negative diffusion coefficient. Did we say dx or we said simply d? Okay, we'll write it d. D, then del C del x. Want to utilize them now, okay, to develop some kind of relationship or something called equation of continuity or equation, advection diffusion equation or something. So for that, let's see, suppose I have a strip and we'll try to do it in one dimension. Okay, and my flux is in this direction, okay, and the area is A, okay, and the direction, this I am calling this as x, okay, the width of the strip, okay, let's call that as the delta x, okay, and then C is a concentration at this point, okay, C here, okay, that is at x and t, okay. C has two domain, okay, the concentration, it can be function of x and it can be function of t, okay. And here on this side of the strip, C will be at time x plus delta x and t, okay. Just to make it more clear, I can, even if you like, I can make it little look, to give it a solid look. Okay. Now I want to write the mass balance about the strip, okay. Writing mass balance. So I can say the accumulation inside the strip is input minus output, and say the flux which I am talking about here is, let's say, J. Okay. So what I can say about the accumulation is the concentration at x times T plus delta T minus concentration at xt. Okay, that is a change in concentration you have. I must convert this into the mass per time. Okay, so what do I do? Area times del x. Okay, and time is delta t. That is the accumulation part. Okay, all right. This is something, again, something similar to del C by del T, but we are talking against this strip. Okay, the concentration, we are talking accumulation. How much is accumulation rate? Okay, concentration at T plus delta T minus concentration at T times delta T. So concentration per second or per time, but we are interested in mass balance. So area times delta X. Is that all right? Okay. This must be equal to, I can take the advantage of J now. Okay, what do I do? J at the time at x t, okay, and minus J at x plus delta x. Okay, what do I multiply here to get the same units as this one? Flux is what? Mass per time per area, right? And what I want is mass per time. So I multiply by area here. See here if you agree with this. Is it all right? Well, we'll do it once again. J. What are the units of J? Mass, area, second. Okay. So if I multiply by this area, I am getting mass per second. Mass per second in, mass per second out is mass per second accumulated, right? That also is mass per second, mass per second, mass per second. Okay, is that right? All in agreement with me? Okay. So this area will go off from here. Okay. This one, if you agree, I can write this as T. Okay. Times, let's say I am still maintaining the delta x here. For J, what can I write? This plus this, that is the total flux. Flux due to advection and flux due to diffusion. Okay. So if you agree with me, I can write here Cu, okay, minus d. Okay, since we are writing still in delta, so I'll write this as delta C over delta x. Okay, this is evaluated at what? At x. Okay, so at x minus Cu minus d del C over del x, delta x rather, evaluated at x plus delta x. Any problem so far? Yes? In this, in here, what is saying? At the outlet? X plus delta x. See, where is it? Where is the C I am talking about? Concentration is in the strip. Concentration is in the strip, not at the faces. Right? The concentration is in the strip, not at the faces. I am not talking about the faces. Concentration is in the strip. So that how will concentration in the strip will change? So concentration strip will only change because of change in time domain. Okay. So this is concentration, this accumulation in the strip. Okay. If you like, in strip. Okay. And then suppose if we take the limit, okay, delta t tends to 0, delta x tends to 0. Okay, let's see what we can write. Okay. Okay, so this I have this minus this, so I am getting this as the minus, that will be plus del x of d del c by del x. See if you are getting the same expression or not. Okay. You also have to make sure what I have written is correct. Okay. Is it minus sign? You see everyone how the minus sign comes here? For derivative, it is derivative at x plus delta x minus the concentration at x, whatever. Okay. But this you see here, this you have, this term is plus. Okay, minus this, or have we got it the other way? We got the other way. Let's see, we'll do it again. Okay, let's see. Should be minus. Do everyone see that? That will be minus? Or we need to do some expansion? You see that's minus. Very good. So this will be minus. Okay. Alright. Or minus. Suppose I say u is not function of x. It means if I am traveling along the direction x, the wind speed does not change in my case. So that is the approximation I am taking, or that's the assumption I am making. So u is out, del c by del x, and I am also saying the diffusion constant is not function of position. Okay, so this also can be taken out. So d or plus u del c by del x minus equals to 0. And if you agree, I can write a three-dimensional form of this one. Okay. But before we do that, you recall this D we are taking this as the molecular diffusion. Okay. So, now this D will replace it with the turbulent diffusion, because in the atmosphere most of the time we encounter the turbulent diffusion. Okay. Hoping that the theory remains the same. So, I can write this plus U del C by del X minus normally the turbulent diffusion we are talking in the X direction only. So, that is I can write the turbulent diffusion coefficient Kx Note that Kx is the turbulent diffusion or the diffusion term in the atmosphere, and the units of the Kx will be the same as that of D, because we are simply replacing the d phi k. Okay. Now, if you agree, I will generalize this equation in the form of 3-dimensional equation, because our air thing is always 3-dimensional. Okay. This equation is valid even for the water system. This will be valid even for the river system. Okay, 1-dimensional thing, but we will make it 3-dimensional and try to write in 3 dimensions. So okay, minus Kx square C by del X square minus Ky del square C over del Y square minus Kz okay, and this what is our 3-dimensional advection diffusion equation. Okay. This is our 3-dimensional advection diffusion equation. And what you can do is that if you agree, I can write that these terms together are my advection term, or which is causing advection diffusion and advection transport, and this term I can write this term as diffusion or turbulent diffusion. I am not using the word turbulent diffusion, what is that? Okay. Here we have not added the term source and sink. Okay. To keep the life simple, we have not added the term source and sink. We are not adding any more emission, okay, as a source, but soon we will do that, the same thing. Okay. Some of you, now let me explain. U is the velocity in the x direction, V is the velocity in y direction, and Z is the velocity, W is the velocity in the Z direction. Similarly, the turbulent diffusion coefficient in the x direction, in the y direction, and in the Z direction. Clear? Okay. And to give you a little feel of the system of coordinate system